But important parts. What's that? Enzyme. What's this? Give me another name for substrate. Reactant. Okay. This is product. This is the key. What is that? The enzyme substrate complex. Remember, for an enzyme to facilitate a reaction, the substrate of the reactant has to be bound inside. The amino acids have to facilitate or stabilize the transition state for that reaction to occur. Okay? The problem is, when I mix things together, that's hard to calculate or to know. I know how much enzyme I put in, and I know how much substrate I put in because that's the beginning. Then it mixes all up, and there's a dynamic of the biology happening in which the substrate binds to the enzyme does, the substrate, the enzyme gets converted, or the enzyme converts substrate to product, the product is released. There's all this dynamic binding occurring. And that dynamic binding is the kinetics of the process. And so the ES complex is somewhere less than 0, but not more than the total number of enzyme that's in there. And it's somewhere in that mix. Now, the big assumption is that we get to a place called the steady state, in which it's a dynamic equilibrium, and the concentration of enzyme substrate in all of its dynamic, both coming together and breaking apart, is constant. So what we defined were the two things that made enzymes come together and two things that made the enzyme and substrate come together, and the rates that I actually had enzyme substrate break down. And so what we did was this. We took the total enzyme that was put in the test tube, the enzyme that was free with no substrate, and the enzyme that is bound to substrate, and we kind of substituted this in. So we have 3 different enzyme states, either enzyme bound to substrate, the amount that was total that we added, and the amount that is free. Okay, and so the free plus the enzyme plus substrate equals the total. All right, and then we had several equations, okay, for the formation and for the breakdown of ES. We could set these equal because of our assumption, the steady state. The rate of breakdown and the rate of formation is equal. Okay. Then we did some sort of math. We distributed this over this, and we distributed that over that. Just simple multiplication. Then we had something that was negative on this side, and so we added it to the other side, so it's all positive. We also functionally put ES, ES, ES all on this side of the equation. Okay? Because ES is what we don't know. Everything else we kind of know. All right? We got to this, and we said, oh, there's ES all over the place here. So let's factor ES out. So if I factor out the K2, the K minus 1, the K1 ES, the K1 and substrate, and I factor all those things out, I get to 1 ES. That's what I'm looking for. Okay? What is K1, K minus 1, and K2? When we use K, what are we actually talking about? A rate. A rate is a number. It's a numerical value. And there is a value at which it processes and all of these different, and you can go back and look at the arrows. Okay? So, substrate, I know how much I put in. Substrate, I know. Total enzyme, I know. And then I've got rate constants. And so, to set this equal just to ES by itself, we divide this factor on both sides, and we get ES and rearrange it. Starting to look a little bit better. Okay. And so, but the rate constant is on the top and on the bottom. And so I divide everything by K1, the top and the bottom. So I can, in this case, cancel that out here, cancel that out here, Okay, and then what I get is this group right here. That is rate constants. They're all numerical values. And if I simplify that, that's a simplification. The k minus 1 plus the k 2 divided by k1. All right, those are all rates. So just a little simplification. I'm going to simplify it one more step. I'm going to define something. If these are all numbers of rates, then I'm just going to call and combine them and call them a Km, a rate constant for all the things that are going on. Okay, and it's M because it's the Michaelis mitten. All right, so Km is going to be important. Km takes into account all of the rates. And so if I substitute that, that looks a whole lot more simple than some of the things that we've looked at this moment in time. All right. So this is a big key. The steady state was a big key. Here's the third big key. The velocity of how much is being produced. Ultimately, the velocity or the production of product is equal to the ES complex times the rate that produces product. Okay? That's at K2. And so, if I know this, if I actually want to know how much product is produced, I take K2 and multiply it by ES. Okay? I'm going to go back one slide. I have just defined ES as this big old chunk. Okay? And so, instead of having ES, which I don't know, I put in that big chunk right here of things that I do know. Okay, so I've changed it from an unknown to known values. Now that big chunk is nasty looking, so I'm going to rearrange it a little bit, and I'm going to do K2 times enzyme total is equal to substrate on the top divided by substrate plus Km. And eventually I do want to know what the velocity, how much product is being produced. Okay. Big time. All right. The rate constant is a numerical value. Okay. The concentration of substrate is a numerical value. Okay. If by chance the substrate is much greater than the Km, okay, let's say if the substrate concentration is 1,000 and the Km is 1, okay, then you get 1,000 on top divided by 1,000 on the bottom plus 1, that equates to approximately 1. Okay? If the substrate being so much greater than the Km, then if I go back to my equation, okay, I go back to my equation right here, if this is true, if that becomes 1, then the velocity is only dependent upon the K2 times how much enzyme is there. We're going to define that as being Vmax. Okay? What this is saying at this step is this. If you have so much substrate in the mixture, and you have a little bit of enzyme, then every enzyme, the total amount of enzyme will be bound to substrate because there's so much more substrate. And if every enzyme has substrate, then we will reach the fastest we could ever be. Okay? Because we now define, the rates of it making and breaking aren't important anymore. It is now just the rate of the product formation. We're going to call that Vmax. And so, the velocity at any point is equal to the maximum velocity that it can ever have times what concentration of the substrate is divided by what the concentration of the substrate is plus the Km, the rate constant. This is the Michaelis-Menten graph. This is the equation that governs that graph. Okay? And so the graph that you see here is this mathematical equation. Okay, I'm going to show you something. I'm going to say this. If the substrate concentration is equal to Km, okay? If the numerical value of the substrate concentration is equal to the rate constant of this Michaelis-Menten, okay? What does that do to the equation? Well, the velocity is equal to Vmax times the substrate on the top, the substrate on the bottom, plus, if I said this is equal, then I can just substitute in the substrate on the bottom, because that's what I defined it as being. The velocity at this time is Vmax, okay? One substrate on the top, two substrates on the bottom. Substrates cancel out. The velocity is 1/2 Vmax. Okay? So mathematically, if the numerical value of substrate is equal to the rate constant, then I get 1/2 Vmax. This is wonderful. A rate constant is kind of hard to determine. But this equation does this. If I know what the Vmax is, I go to half of that. Then I can go to the graph, I can read down, and whatever this numerical value is the Km. I can determine the Km, the rate constant, by looking at that graph. Okay? Now, here's the deal about Michaelis-Menten. What is Vmax? Well, it approaches Vmax. Never quite gets there. You know, it will become linear. It becomes an asymptote that never actually reaches that point, but you get the Vmax. That's good. I can take half of that. I can put whatever number and divide by 2, right? We got that. I can read the graph. And then I can go over here, and then I can go down. That's a wonderful estimate. Okay? And that's a good way to estimate the Km. It's not the best way to actually determine the real value. Okay? Now, this whole thing is dependent upon this assumption. I said if the substrate is equal to Km, that's what the math happens. But I can actually calculate what the velocity is any point on this graph by saying, what happens if the substrate is 2 Km? I can do the math and actually figure out what the velocity is. And if you do enough points, mathematically, you could get points along that entire curve. Okay? So when S is equal to Km, it's 1/2 Vmax. And I can get that concentration. Now, that's great. You get this curve. That's what we see. But it's hard to get numerical values from that. So, Lineweaver-Burke took the math and did it a little bit differently. It took Michaelis-Menten's graph and its mathematics, and what they did was they took what's called the double reciprocal of it. Okay? And what the double reciprocal plot entails is a much simpler graph to interpret. So, what do? Let me go back 1 second. To get this, I plot the concentration of substrate in whatever unit it is, and I plot how much material is produced over time. So that's what you actually plot on the graph. Here, what you're going to plot is 1 over the substrate, whatever that substrate concentration is, and you plot 1 over the velocity. This is where the double reciprocal comes in. Okay? And this is what happens to that graph. How many points do you need to define this particular graph? If you actually had to go into the laboratory, how many experimental values do you need to take to get this graph and produce this graph? A bunch, right? you have to have a couple of points, okay, to get where this linear part is. You got to get a couple points to show where it's curving. Then you have to get some points way out here to make sure you get where it maxes out. And in an experiment, when you design an experiment, do you take one single value here and one single value there and one single value there? No, you never take 1 point. Should you take 2 for each of those points? What if one's different? Can you statistically do an analysis to know if any one of those is good? Not really. 3, you can actually start doing some statistics, but not important ones. 4 or 5, okay. All right, 4 or 5, 5 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's a lot of test tubes. That's a lot of in laboratory experimenting to do. Okay. All right, how many points do you need to take to get this graph? 2. You'll get a perfect line. But can you do any statistical analysis on 2? No. You need 3, 4. You can actually get 5 points and actually do a linear regression to know how good the fit of the line is to that data set. And so you now can do 5 points in 5 trials, so 25 points versus 50, and get a much better analysis of the actual information. So 5 points. What you will do is look at these 2 places. The intercept right here will give you the numerical value 1 over Vmax. The numerical value here is minus 1 over Km. If you can get a line, you can get an equation of the line. And if you can get an equation of the line, you can solve for both the x-intercept and the y-intercept. And you can get those in numerical values. You take the reciprocal of one, and you take the negative reciprocal of the other, and you can determine Vmax and Km very, very easily. Much easier analysis to do with this particular version of the equation. And so if you're actually asked to do analysis, most likely you're going to be doing a Lineweaver-Burt plot rather than a Michaelis-Menten. The slope is actually Km over Vmax, although that's not easy to parse out what numerical value it is, but the intercepts are very easy to determine. Okay. Now, this assumes that you know how to plot. Okay? And so, the quiz that I'm going to give to you is to actually calculate values using this kind of math. All right? And next time we come in, I'm going to give you some time to work on it in class. You won't have to turn it in class, but I want you to know how to plot things. And you think that's simple, okay? But I think here's a really, really bad thing that happens. We have been taught, and the analysis is much better if we plot it on Excel. And it puts the equation on there. But quite often, the scales, sometimes it defaults to scales, which might not be the exact things that we need. And if we use the computer, we actually forget how to actually do this. So I'm going to get you a piece of paper, a piece of graph paper. I'm going to give you some data, and I will give you a ruler. Okay? I want you to physically be able to produce these graphs on a piece of paper so that you understand. Now, what I will want you to do is work that in class and try to do that, but then follow that up with the Excel and see, did your piece of paper even look anything like the Excel sheet? And if you can't make them look the same, one of them is probably wrong. I'm going to assume at least one of them is right, okay? You have to decide which one is right, okay? If you get both of them looking the same, by analysis, you'd probably think you probably are precise. Okay, you can get them to look the same. Still, I'll tell you if you're accurate or not, all right? And so, but I want you to understand that. Km itself, all right? Km is a rate constant. We know that 1/2 Vmax is Km, okay? What this really is a measure of, okay? Vmax is when, how much of the enzyme is in the ES complex. I reach Vmax when all of it, 100%. So Km, if it's equal to 1/2 Vmax, how much of the enzyme is being filled? Half. You effectively have half binding, okay? And this is what happens in biological systems. Every binding pocket, in this case an enzyme, has an affinity. If you put in a very low concentration of substrate, you're going to get a certain percentage bound. And as you increase the substrate concentration, the percentage increases until you get 100%. Okay? 1/2 Vmax, a lot of people use Km as a good measure of the binding constant of an enzyme. Although, if you actually talk to someone who studies enzymes, Km is not a measure of its binding affinity, because Km involves both the bonding and the release, but man, it's so close. Functionally, it's a good idea of how well things bond. And so if something has a Km that is in the millimolar range, in biological systems, that doesn't have a lot of affinity for whatever you're binding. But if you have Kms in the nanomolar range, that means half of the enzyme is filled when you only get in the nanomolar concentrations. That's high affinity. And so it is a useful estimate. It is not a binding affinity. We can actually talk about a dissociation constant for the binding itself, but those numerical values are almost so close that functionally we use it that way in terminology when we talk about it, but know that it actually isn't exactly the same. We can talk about turnover number, okay, or the rate of catalysis. This rate of catalysis is actually the value K2. It's the number of substrate molecules converted into product over time. Okay, this is determined when enzymes are fully saturated. So sometimes you can see the rate constant Km. Sometimes you will see K-cap being talked about, or the rate of catalysis. Okay, and this means that all enzymes, however, is filled with substrate. Now, there's one kind of slight issue on this slide, okay, that you probably need to understand, and that is right here. Okay. Most enzymes have one binding pocket. That is not necessarily always true. And so there can be enzymes that have multiple binding pockets and multiple active sites. And so that changes the dynamic just a little bit if they have multiples. You can also calculate a round of catalysis, how many seconds it takes to convert one molecule. That's taking the rate of catalysis and taking the inverse of that. All right, is there a limit to how fast an enzyme can work? Okay, there is. Okay, there is a rate at which enzymes cannot go any faster. Okay, but here it's more of a philosophical issue than actually can the enzyme actually work any faster? All right. The assumption is this. Okay, the enzyme rate is I let go of a product, I pick up an enzyme, I pick up a substrate. I let go of a product, I pick up a substrate. And if I can get to that point, as soon as I let go, I can pick up. I am now measuring only the rate of conversion of product. That's where I get to Vmax. Okay, enzymes are very quick, and so the fact that picking up the substrate really isn't in the play unless the enzyme really does work fast. There is a rate or numerical value at which we reach called kinetic perfection. We don't know if the enzyme works any faster or not. What we get to is the rate limiting step of things diffusing through water. Okay? And so you cannot go any faster than the substrate actually flowing through the water itself. Okay? And so if you reach the rate at which the speed of things moving through water is the rate limiting step, then the enzyme is at kinetic perfection, and it might work faster, but it can't get substrate any faster than how fast the substrate can diffuse through water. When you reach a kcat divided by km of 10 to the 8th to 10 to the 9th per moles per second, you have reached kinetic perfection. There are some enzymes that do reach kinetic perfection and work at that rate. Any one enzyme cannot go any faster than that. But rates can be faster if you have multiple enzymes working together. So if by chance you have a process that takes 3 enzymes to produce product, so you start as a substrate and you end as a product, but you have to go through 3 different reactions, and you multiply the rates of those 3 reactions, you should get a maximal speed at which you can do it. If you actually have the enzymes bound to each other, you can actually have the entire process go faster than the rate of diffusion, because there is no diffusion that happens. One enzyme hands it to the next enzyme's active site with no diffusion, and you can increase the rate if they are bound together and you have a process occurring. Very rarely do we ever see this, but that's the way that you can get around. A lot of things within the biological system is not an enzyme that finds it, lets it go, diffuses until it hits its next enzyme, and then it does its reaction, and then it diffuses to its next enzyme. Many of our pathways have all of the enzymes bound together, and the substrate is moved from one to the next, to the next, to the next, as it goes through the whole process. And so we increase efficiency that way and specificity that way. All right, enzymes are great. Enzymes work, but sometimes enzymes work too fast, and so we have to slow them down. Now, in the body, there are lots of ways to slow enzymes down, and we use inhibitors that are natural. But there are times in which a pathway is working that really shouldn't be working, and so we introduce a molecule to inhibit a certain pathway. We call that molecule a drug. Or if you go to the natural health food store, we call it a supplement. Okay? But it really is a drug. It's just one that hasn't been characterized, nor identified, nor purified, nor regulated. But it's much more healthy. Okay? And so these small molecules tend to inhibit enzymes. And so there are 2 main types of inhibitors: reversible inhibitors, which we've got a whole bunch of those, and an irreversible inhibitor. Okay, what do you think about when you hear irreversible?
Death.
Death. That's exactly what we're going to do. Okay, we're going to kill the enzyme. All right, in some cases that's a very appropriate part. But let's say we kill the enzyme that breaks down glucose. Does that seem to be good? No. What would the body have to do then if I kill the enzyme that starts the breakdown of glucose? If I killed that protein, that enzyme. Doesn't sound great. But for the protein, or the cell to start that process again, I got to go all the way back to the DNA. I got to tell it to make a copy. I got to tell it to translate. I've got to make a brand new protein. It takes a long time to get that enzyme back and running. Okay, but I still have the DNA. I can still make more, and the cells do that sometimes. Okay. Other times, I'm going to have a reversible inhibitor, in which I give a drug for a little while. It will stop the enzyme a little bit, or maybe completely for a short period of time, and then as that drug clears through the natural process, then that enzyme starts functioning. And so these are ways in which we will inhibit enzymes with small molecules. So E is an enzyme, S is a substrate, P is a product, and now I'm going to introduce I as an inhibitor. All right. Inhibitors, okay, that are reversible tend to be this. They will bind tightly at the active site, and then they will become covalently linked to the enzyme. And remember, there are certain amino acids in the active site that facilitate the reaction. Sometimes there is an amino acid side chain that actually reacts with the substrate as part of the process. And so it can actually physically become linked to the substrate in the conversion to product. Our inhibitor is going to bind to that active site and become covalently linked such that it will not diffuse away because now it's covalently in the way. And one, you can't get anything bound in there. You cannot make ES complex, so you can't make product. And you've destroyed the enzyme's actual side chain that does the reaction. So an example of this is diisopropyl phosphofluoridase. Ooh, that's a mouthful. DFP. All right. And this enzyme is one that binds to an active site that has a hydroxide. Okay? And so, what happens is the hydroxide will react with the DFP, the fluoride ion will fall away as a leaving group, and now this becomes covalently linked, and it doesn't fall off. So this enzyme will kill, or that inhibitor will kill that enzyme, and it will never be functional. Where we use this, okay? Remember one time I told you if I need to isolate one protein out of a whole cell, what do I do first to the cells? You break them all apart, right? Well, here's the problem. The cells inside of them have proteins that break down other proteins. When you break that apart, usually those proteins are sequestered, and I don't want to break everything down, okay? But when you open everything up, these enzymes float free that are going to break down other proteins. Okay? Well, I now put them all in suspension, they all get together, and now my protein's being chewed up. One of the processes while I'm doing that breaking apart the cell is add this particular molecule into the mix to stop all enzymes that are degradative. Okay, they're called proteases, the enzymes that break down proteins, so that I don't destroy any more protein than I need to. And so this is a inhibitor of proteases, of proteins that break down other proteins. That is one way we can inhibit. All right, what slide number am I at? What is it, 37? 37. Okay. All right, we're moving ahead. Moving along. We will get together on Friday. We will have the activity. Bring your trusty handy-dandy calculator. Yeah, if you would also print off the assignment, but I'm going to give you a piece of graph paper and I'm going to bring in some rulers. I want you to attempt to do this without putting it into Excel first. And then